Wow, it's great to be here and seeing number of registrations, I think crossing 1,000. That's just incredible. I remember in Monterey, when we first had the very first workshop, we just invited people. I had no clue how many would show up. And I think, I actually checked, it was 144 people who showed up, and it was packed, it sold out. Never idea how popular this would become. So I'm always amazed every time we do the next one of these, and it just keeps getting bigger and bigger and bigger. So today, talk about RISC-V. So Rick already gave you an introduction. I'm going to skip over these pretty quickly. So, I think my summary of this, it's a high-quality, license-free, royalty-free ISA. What that means is that you don't have to pay to get an architecture license. Now, if you go buy a commercial core from somebody, they'll probably charge you something. But if you want to go build your own core, you don't have to pay anybody anything. The standard is maintained by the foundation. And we really designed this to be suited for all types of computing systems. Everything from microcontrollers to supercomputers. And accommodating that breadth of use cases is one of the challenges in RISC-V. Right now, there's many proprietary open source cores, and we have this rapid uptake everywhere. And there's a big and growing software ecosystem. And it's still a work in progress. RISC-V is new. It has only been around for a little while, only 4 years out in the wild, out of Berkeley, 4 years before that. So there's still a lot left to do, but it's already very capable. And I think this year, looking into 2019, what's exciting is seeing actual commercial products using RISC-V appear for the first time. So just a timeline. We started back in 2010. The first tape out was in 2011, 28 nanometer FDSOI, Raven 1. We did a bunch of other work, first Linux port. 2014 was really a big milestone when we went to Hot Chips wearing these t-shirts and made a big noise about RISC-V. And that's really where the sort of external-facing notion started, that RISC-V could be a thing. We had the first workshop, the one I just talked about, beginning of 2015. And we created the foundation back in August 2015. Now, some of the big highlights, I think, so other big milestones in RISC-V was mid-2016 when NVIDIA announced that all of their future GPUs would use RISC-V for their on-chip microcontrollers. That was a really big endorsement from a major industry player who spent time evaluating this ISA against others. The commercial software started appearing in 2016. And the end of 2016, we saw the first commercial RISC-V SoC come out from Sci-Fi, the FE310 microcontroller. Can keep working on the specs. And another big announcement last year, at the end of last year, Martin Fink announced that Western Digital would be moving all of their devices over to RISC-V. So, a couple 1 to 2 billion cores moving from existing architectures over to RISC-V. Those are all big deals. And then beginning of this year, we had the first Linux-capable SoC come out from Sci-Fi commercially available. And over this last year, we've seen a few more chips coming out. I think next year, you'll see a lot more silicon for RISC-V. So there's been this transition from Berkeley out to the world, and this is the first summit. So we decided to move to this one large summit format to accommodate demand. But there's many, many other events happening all around the world, in all parts of the world. It's amazing to see. So why is RISC-V so popular? Now, I think engineers are probably the worst people to figure this out. They sometimes don't see the forest for the trees. It's not happening because some benchmark ran 10% faster or some implementation was 30% lower power. Those things might happen. But that's not why this is happening. The reason this is happening is because this new business model really changes everything. So now in the industry, you first pick your ISA, then go figure out how you're going to get the cores. Previously, it was pretty much you picked a vendor and you got the ISA they gave you, right? And you can add your own stuff to these cores without permission. So it's really this open up for innovation by allowing people to change the cores, but more importantly, giving people freedom on how they source their cores. They can get proprietary cores, open source cores, build their own cores. So this is why everybody's excited moving in there. You should not look feature list by feature list of this core versus that core and decide to go with RISC-V or not. You should be thinking long term, where is this industry going, right? And I think these things are driving RISC-V forward. Now, what you'll find right now in any given application, RISC-V might be fine, it might be superior, or it might be lacking some features or missing stuff. What we've seen over time is whatever's broken, missing in RISC-V is going to get fixed. And the reason is the momentum behind the change in the business model is really what's driving this. Everybody wants this to succeed because they want this different world. And they're going to make all this stuff happen. So that's really the message. If you think things are missing, broken in RISC-V, one strategy is wait a while, or better, join in and help us fix everything that's not there right now and make this a better system. So our modest goal is really, become the industry standard ISA for everything. So I'll just go through where we are with a lot of the ISA efforts. I think one thing it's important to do is help you understand what is the RISC-V ecosystem. How does it work? Well, the center of the ecosystem, you have the RISC-V Foundation. So the constitution of the foundation sort of states it will do these three things somehow. It will maintain publicly available ISA specifications. They're always freely available for anybody to download. It will also maintain a golden model, and it will also maintain compliance suites. And all of these are freely available for anybody to go download. So this is at the heart of the RISC-V ecosystem. Now, as Rick mentioned, the foundation does not manage core designs. You don't go to the foundation to get a free RISC-V core. That's not how it works. So the ISA spec is really this interface between software and hardware. And on the hardware side, there are many, many, many implementations out there. So there are open source cores. People sometimes confuse RISC-V and say RISC-V is an open source architecture. That's actually technically incorrect, right? RISC-V is a free and open specification. Because it's free and open, it means you can have open source cores. It enables there to exist open source cores, but it doesn't. RISC-V by itself is not an open source core. It's just a specification. So there are many open source cores, more appearing every week, different feature sets, different goals. But there are also a very large and growing number of commercial core providers. So these are folks who will sell you a supported piece of IP that's been designed, verified, tuned, will comes with commercial support, documentation, integrated into a chip. So the quality IP that you can use in your advanced design without worrying about your chip falling over. And I think I have probably an incomplete list. I imagine there's several more that I've forgotten or just got formed last week to add to this list. But I don't think there's ever in history been a single ISA that's had this many providers, commercial providers of the ISA. Right? That's already the state right now. So in addition to open source cores, commercial cores, the thing about RISC-V, it gives you an open architecture license. You can go build your own core. So for example, NVIDIA, they're building their own core. It's an in-house core they're designing themselves. Other companies, Western Digital, others, are also building their own cores in-house. And for many companies, their strategy is, well, this is great. Project by project, I can pick how I source the core for that project, right? So I can use an open source core, I can use a commercial core, I can build my own core. And this is really one of the freedoms in sourcing the cores that's really driving people to this model. So now, RISC-V is a spec. It sits in the middle of the ecosystem. It provides a stable interface between software and hardware. And what this means, all of those hardware implementers get to share all the hard work that's done by the software ecosystem providers to bring up this ecosystem. So there's a lot of activity in the open source software domain, things like GCC, Linux, and RISC-V is now a mainstream supported architecture. And so you can just go download from the regular distribution channels and get GCC compiler RISC-V support, or Linux with RISC-V support. And there's many other open source projects that are also porting to RISC-V. But it's not just about open source software. There's commercial software. So I listed just a few of the vendors who are providing commercially supported software to help people do development on RISC-V. So for embedded tools, for example, Lauterbach and Sega support RISC-V. Various others provide commercial operating systems that are not open source. So again, I'll emphasize RISC-V is not an open source processor. It's an open specification. The great thing is that allows there to be open source, but doesn't mandate that everything is open source. If you build your own core, use it on your chip, nobody's going to require that you open source that core. Okay? So that's the overall ecosystem. So I'm going back to now I want to focus on what the foundation actually, its core mission is, which is the specs, the models, and the compliance suites. Right? Let's see how we've been doing. A lot of progress this year. So the main focus in 2018 has been on ratification, getting all those specifications originally written by people at Berkeley and other places and contributed by many people after that, and getting them to a form where we can say this is the official foundation ISA standard. So the good news is that the vast set of the core ISA that originally came from Berkeley but has been modified a lot, that now is out for public review, and that public review period actually closes December 21st. So it's out there for ratification. A big deal is the memory model was ratified. This was a large undertaking, very complex, involved the world's experts on memory models. This is now actually being ratified. It's the first thing to actually go through ratification. It's kind of curious. The most complex thing is the first thing we ratified. I'll talk a bit more about that later. The debug spec also closed public review, 0.13, and that's now awaiting the board to ratify that, to approve that. Big announcement. So the privileged architecture went out for ratification today. So the public review. So I should say, when we do the standards, after the groups are finished, agreed on a draft, they then have a mandated period where it's open for public review, which means anybody, absolutely anybody, can give comments on the spec. And the working group has to respond to those comments. They don't have to do the changes people suggest, but they have to have a response to anything in that public review period. So now the privileged architecture 111 went out for public review today, and that public review period will end January 25th. So the goal really is, and we seem to be on target, we'll have all of the core ISA, the central parts that everybody has been relying on, should be ratified at the start of 2019. And really everything else will build on this. So now we have official foundation standards for all these components. One thing I'll talk about is we like to talk about things being frozen, and when the Berkeley spec came out, at Berkeley we said, this is it, it's frozen, we're not going to work on this anymore, it's done, just use this. There have been some small changes. I thought it's interesting to go over those. So the memory model in particular was something that was underspecified in the original Berkeley spec. So a big group put a lot of work together in doing that. In the floating point side, there were some tweaks to the way you represent NANDs and NAND boxing. And some of the instructions actually did change meaning, which was the fmin and fmax. And that was because of changes in how IEEE was managing the floating point standard. So we tracked those. One other thing that happened is we previously considered the control status register instructions part of the base. We've now moved those out into a separate extension. So we use Z now for other standard extensions that don't fit in the single letters. So one other bigger one was that fence.i, which is the way the instruction stream is synchronized with changes to the data memory, we standardized that instruction but moved it out of the base. And the reason is that over time people realized that there were issues that fence.i isn't the right primitive to use in some platforms. In particular in Linux, it's been taken out of the user ABI, and we now rely on a OS call to implement fence.i, possibly using the hardware fence.i underneath. So there's a lot of interest and work in how do we provide a better iCache coherence mechanism in the future standard. So it's part of this ifence.i, which has been ratified. And for now, this is a thing to use, but people are working on an alternative there. Commentary has been improved a lot. We removed a lot of platform mandates. One of the things is the golden model. Originally had a C model, and that's been replaced by this formal model. The formal spec group, they've completed actually several formal models that are all checkable and work with each other. And another thing that happened in the formal group is developing a feature way of specifying features. In the ISA, there are many options. It's very modular. Some of those require other pieces. And so the formal group has developed a way of managing that feature set and making sure you have the right dependencies in there. I think this will be important going forward. There's also a follow-on formal group will probably be formed to deal with concurrency. So the existing formal model is single thread, and we need to look at concurrency and interaction with RVWMO. So compliance suites, we've been improving the framework for the test suite. A lot of work here, a lot of companies involved delivering components. There's a little official RFP, and we have Gary Crumley from WD, who's working as the technical program manager to drive this work forward. We're also being, one announcement you probably have seen is we're now collaborating with the Linux Foundation, the RISC-V Foundation, working together, leveraging the great resources of the Linux Foundation to help, and in particular managing code bases like the compliance suite, which will be the largest code base that the foundation actually manages. So I mentioned several times about the memory model, and I just want to announce that we decided that on the board we should have regular awards for people who've contributed a lot to RISC-V. And it was pretty clear there was one individual in particular who deserved recognition this year, for driving this forward. So although the memory model involved a lot of work from a lot of experts, put a lot of time in, just want to say Dan Lustig from NVIDIA, really, we thought he was just, did an incredible amount of work here, and we decided he should be the winner of the inaugural Foundation Board of Directors Award for contributions to RISC-V. So Dan, you want to come up? Hey, Dan. Okay, so the citation reads, for his leadership and technical contributions in developing the RISC-V memory consistency model. So Dan. Okay. Thanks. Cameras. All right. Okay. All right. Thanks, Dan. Yeah. So, yeah, I want to thank everybody else who's also involved in the memory model, but Dan was the hard taskmaster got everybody to actually finish. So the most complex thing was the first thing to be ratified. So thank you, Dan. Moving on, a few other things I'd like to talk about, remaining time, is fragmentation versus diversity. So in RISC-V, often people attack it and say, well, this, all these pieces of it's just going to be fragmented. And I think you have to separate fragmentation from diversity, really. And we should start using these terms in our, when we talk about this. So fragmentation is when you do the same thing in multiple different ways, right? But diversity is when you're supporting many use cases. So RISC-V was designed to support specialization. By definition, that means different cores are going to have different features. That's the whole point, right? But fragmentation is really when two groups or two organizations decide to do the same thing in different ways. And that's what's bad, right? So doing the same things in different ways is bad. Supporting many use cases is good. So do not imagine that a single RISC-V core is going to have every single possible feature ever all combined. That's not really the design goal. Now, some platforms like Unix land tends to want to have very stable because they have so much software to support. And then there'll be much, much less diversity in the platforms. It has to be. But embedded, really the use case is make things really specialized for that particular use case. So ongoing ISA extensions work. So what's coming up? So things that have been in progress. So the fast interrupts, the click working group. There's a pretty complete draft, and that's getting to the point where it's pretty much stable, ready for people to try implementing, maybe ratifiable this year. Vectors have been taking a long time. There's been many tumultuous changes around a theme, but it's getting stable, and we hope to get that ratified in 2019 as well. The hypervisor has been pretty stable. Crypto, trusted execution environments, bit manipulation, J extension, the DSP extensions, the P extension, and SV128. These are all things that are ongoing and working. So one thing I did want to talk about as well is standards expectation management. So the existing base and standard extensions, they were 8.5 years in development. They're only now being ratified, right? So it took a while to get those through, and they've been in process for many years and with many implementations. When you work on a large ISA module, it takes time, expert input. Experts disagree. Community wants perfection. It takes time to work on these things. So debug spec is when we started in the early days of the foundation. That took nearly 3 years to come together. And there's more to do on top of the base. It's just a set of features. Vectors are already 3 years in process to get this done. So these things take time. Now, small updates and fixes can happen faster. But I think we're going to have to look at the processes in the foundation to cope with the real standards lifecycle, right? These things take a while. So, some things that happen is you define your need, you gather inputs, hold meetings, you get whiteboard level design arguments. People, argue in PowerPoint or mostly ASCII text, I guess, arguments to and fro, finish a draft. Then you have to go build an implementation, and then you have to go evaluate it, build software for it, evaluate it, and then iterate. So all this takes time to go around. And also, we don't want to freeze anything that hasn't been actually implemented and has a software stack built for it, right? So this process takes time. And once you're ready, once you've gone through that step a few times, and multiple implementations exist, then you should be ready for ratification, right? Then finally, deployments, compliance testing, and maybe eventually replacement. We talked about things being stable. A module may be stable, but sometime later in the future, we may decide, hey, there's a better idea for that set of functionality. We'll have to go replace it. So this is something else we should be dealing with. When we do ISA extension work, I think the things to think about is, our implementer is going to build it. This is not an academic exercise at the foundation level, at least, in pushing standards forward. So the implementers wonder, are we going to get more design wins for RISC-V if we add this thing? Does it fill a hole in capability? Does it standardize something that's being done incompatibly today? Does more than one member care about it? Right? These are kind of things we have to do in figuring this out. Can actually anybody work on this? So our proprietors in 19 are do the implementation software stacks with a click, vector, hypervisor. Work on the Unix platform standard. There's enough people interested now in standardizing this. Work on the embedded ABI. Another proposal coming in is help embedded systems by doing a variant that has a floating point in the X registers. And this will also help with code size, which is one issue people are seeing in the embedded space. There's a lot of work going to be happening in compilers, libraries, and additional compressed instructions. The embedded ABI, the original ABI is developed for Unix. We're developing a new one for embedded platforms. The goal is reduce interrupt latency, reduce code size by dropping 128-bit float, and making it compatible interface between RV32E and I. Okay. Float in X, remove the F registers, do floating point operations out of the X. This also frees up some opcode space that we use for further compressed extensions. Embedded code size. I think one of the big things is better documentation. We see a lot of people haven't understood quite how the compiler toolchain works. That's one of the issues. But also the library code needs improvement. Compilers need improvement. And then finally, we also do need to probably add some more instructions. All these are things in progress. So big news is core standards almost all ratified. I think this is a big milestone for RISC-V. The base stuff we all build on is pretty much there. The foundation standard. The software ecosystem is filling out rapidly. And it's time to standardize these platform profiles. As that software ecosystem fills out, they're the ones that we need to define these platform profiles for the implementers to be able to do the right thing. Okay, lots of work ahead. All right, that's it. Thanks.